Welcome to The Explainer. Today, we're going to break down a classic physics problem, Irodov 1.141, that beautifully ties together work, energy, and friction. Now, I know it looks a bit tough at first glance, but trust me, if you approach it step by step, it's totally manageable.
So, here's our roadmap for this. First, we'll unpack the problem to see what it's really asking. Then, we'll grab the physics concepts we need from our toolkit. After that, we'll dig into the forces right at the moment of slipping, calculate the work, and then wrap it all up with the biggest takeaway.
All right, first things first. Before we even think about writing down an equation, we have to really deconstruct the problem statement. Let's figure out what's going on and what we're actually trying to find.
You know, the problem statement itself gives us two huge clues right off the bat. Slowly shifted and start sliding. Honestly, these little phrases are the keys to the whole thing. They practically tell us which physics principles we need to use.
Okay, let's get everything organized. It's always a good first step. Over here, we've got what we know: the mass, the initial length of the cord, that friction coefficient, and the final angle. And over on the other side is our clear goal. What is the work done by the friction force? Simple as that.
So, before we start actually solving this, let's open up our physics toolkit. For this particular problem, there are really three core ideas we need to have handy.
First up, static friction. This is that sticky force holding the bar in place on the plank. But, and this is important, that grip isn't infinitely strong. The problem tells us the bar eventually starts to slide, which is a huge hint. It means we've hit the absolute maximum value of that static friction force.
Next up is the work-energy theorem. This thing is the real powerhouse for our solution. That word slowly is a gift because it means the bar's velocity is basically zero the whole time. So its change in kinetic energy is zero, which means the net work done by all the forces added together has to be zero too. This is a massive shortcut, as you're about to see.
And finally, elastic potential energy. Think of it like a rubber band. As that plank moves, the cord stretches, and all that stretching stores energy inside of it. Being able to calculate that stored energy is going to be absolutely essential.
Okay, now for what I think is the most important part of the setup. We are zooming in on one specific instant in time, the exact moment that bar breaks free and starts to slide. If we can get the force analysis right at this moment, the rest of the problem just falls into place. If we were to draw a free body diagram of the bar, we'd see four forces acting on it. Pretty straightforward. You've got gravity pulling it down, the plank pushing back up, that's the normal force, the cord is pulling on it at an angle, that's tension, and finally, static friction is pulling to the right, resisting that slide. And because everything is happening so slowly, we can pretend the system is in equilibrium right up until that slip. What does that mean? It means all the forces cancel each other out perfectly. The left-right forces are balanced, and the up-down forces are balanced. This gives us two incredibly useful equations to work with.
Okay, pause for a second. Right here, this is where so many students fall into a trap. When you're setting up these equations, there's a really tempting assumption you can make that will just completely throw off your answer. Let's talk about it.
Here it is. It is so easy to just say, oh, normal force, that's just equal to the weight, mg. But look at our diagram. The cord is pulling up a little bit, right? It's helping to lift the bar. That means the plank doesn't have to push up as hard. So the normal force is actually less than mg. I'm telling you, forgetting this is the #1 mistake people make on problems just like this one.
All right, our force analysis is solid. Now we're ready to actually calculate the work done by friction. But we're not going to do it the hard way. There's a much more clever, a much more elegant way to get to the answer.
Here's the strategy. We already know from the work-energy theorem that the total work is zero. Now let's think about the forces. Gravity and the normal force are perpendicular to the motion, so they do zero work. That means the only two forces doing any work at all are friction and tension. And if their total work adds up to zero, well, that must mean that the work done by friction is the exact opposite, the negative, of the work done by tension.
And here it is, the final beautiful piece of logic. The work done by a spring or an elastic cord is always the negative of the potential energy it stores. So, if the work from friction is equal to the negative of the work from tension, that means the work from friction must be equal to the positive stored elastic energy in the cord. This is our amazing shortcut. We don't have to calculate the work done by friction directly at all.
So our whole mission just changed. It's much simpler now. All we have to do is find the elastic energy that's stored in that cord at the very end, and we'll do that in 3 quick steps. First, we'll use some basic geometry to find out how much the cord stretched. Second, we'll use our force equations to find the tension. And third, we'll put those two together to get the energy.
So first, let's find the stretch. If you just imagine a simple right triangle, you can see that the final length of the chord is the original length, L0, divided by the cosine of the angle. So the stretch, delta L, is just that new final length minus the original length.
Second, we need the tension. Now, I know this formula looks pretty intense, but don't let it scare you. It didn't come out of nowhere. It comes directly from taking those two force balance equations we wrote down earlier and just solving them for T.
Okay, we have all of our pieces. We've got an equation for how much the chord's stretched, and we've got an equation for the tension in the chord. Now what we have to do is put them together and get our answer.
This is where it all connects. We figured out that the work we're looking for is just equal to the stored elastic energy. And a handy little formula for that energy is 1/2 times the final tension times the total stretch. We have equations for both of those things, so we just plug them right in.
And now for the best part, the final payoff. We take our equation and we plug in all the numbers the problem gave us, the mass, the friction, the length, the angle, and when you run the numbers, you get our final answer, 0.09 joules.
But look, the real lesson here isn't the number. It's this problem-solving framework that you can use on all sorts of other tough problems. You deconstruct it, you figure out what tools you need, you analyze the most important moment, and then you try to find a clever strategy to find the easiest path to the answer. The smartest path isn't always the most obvious one.
And I'll leave you with one last thing to chew on. We found that the work done by friction was positive. That should feel a little weird, right? Friction usually opposes motion, it usually does negative work. So my question for you is, why, here in the reference frame of the ground, did the friction force and the bar's overall displacement actually point in the same direction? Think about that one. Thanks for watching.